Good day. My name is Al Romig, and I'm the Executive Officer of the National Academy of Engineering and a member of our Aerospace section. And it's my pleasure today to welcome NAE members and our guests to our technical forum to discuss engineering responses to climate change. I thought I would start with just a touch of history for where this topic came from. As it turns out, this is the most commonly requested area for the NAE to engage in that John and I hear from our membership. It was also obvious when we did the survey of our membership in the strategic plan. For the strategic plan, this topic rose to the very top of the list. And so it's quite appropriate that due to the level of interest of our membership, as well as the importance of the topic, that it formed the basis for this year's forum. More than 80 years ago, a British engineer theorized that elevated carbon dioxide concentrations in the Earth's atmosphere would affect global temperatures. To date, this finding remains contested and, more importantly, unaddressed. The National Academy of Engineering and the academies writ large are committed to addressing the impact of climate change. The Royal Society and the National Academy of Sciences publication entitled Climate Change Evidence and Causes, Updated 2020, notes that human-caused greenhouse gas emissions also increase the likelihood of life-threatening and economic devastating events, such as change in rainfall patterns, some areas getting more rainfall than previously, the occurrence of droughts, changing in snowfall patterns, the rise of sea level, and the effect of temperature of the sea on the intensity of hurricanes. Engineers are at the forefront of these lines of effort to both reduce the pace of climate change and remediate its effects. This year's forum speakers will discuss engineering contributions that enhance the understanding of climate change threats to food security and the economy, and offer improvements in energy, infrastructure, and transportation to mitigate impacts. Like the climate itself, their work transcends national borders and yields widespread global effects. I'm pleased again that Deanne Bell will serve as our forum moderator. Deanne is a mechanical engineer, television host, and entrepreneur. Her television hosting credits include PBS, ESPN, Discovery Channel, National Geographic, DIY Network, and CNBC's Make Me a Millionaire Inventor. She is also the founder and CEO of Future Engineers, an education technology company that engages students in online contests and challenges. Last year, her company was selected by NASA to host the Mars 2020 Name the Rover contest. Previously, Deanne worked at Raytheon as an engineer for 3 years in the area of optomechanics. She earned her BS in mechanical engineering at Washington University in St. Louis. Now, let's all welcome Deanne.
Hello. Welcome, everyone, and welcome to the National Academy of Engineering's Forum on Engineering Responses to Climate Change. As Al mentioned, I'm Deanne Bell, and I'm delighted to be the host and MC this year for yet another engaging forum. And I can't imagine a more pressing and urgent topic than the one we'll be discussing today, climate change. As we all know, addressing climate change requires cooperation on multiple levels, from policy to research to changing consumer habits. But the engineering community has its own unique roles and responsibilities. And today we'll be diving into engineering responses to climate change with 5 leading experts. So first, I'm going to introduce briefly our 5 leading experts, and then we're going to go to a series of presentations where we can learn more about this important topic. So I'm going to go through one by one, and you guys can feel free to give a wave when I give a brief introduction. First, we have Dr. Leslie Shoemaker, who's the president of Tetra Tech and an expert in the development of analytics and modeling as decision tools to enhance the environment. Today, she'll be discussing climate equity and blue-green innovation. And then next, we have Dr. Tim Lewin, who's a professor, chair, and executive director of the Strategic Energy Institute at Georgia Tech. He's an international authority on clean energy and propulsion, and will be sharing his expertise on infrastructure implications of decarbonization. Next, we have Dr. Ken Washington. Ken, if you want to give a wave. Ken is Vice President of Software Engineering at Amazon and is an expert in consumer devices and services. Today, he'll be discussing technologies for a more sustainable future. And then next, we have Dr. Mohammad Shahidapur, if you want to give a wave. Mohammad is a professor and director of the Robert W. Galvin Center for Electricity Innovation at the Illinois Institute of Technology and is an expert in electric power system operation and planning. And today he'll be discussing the role of distributed power systems and a quest for climate change. And our fifth panelist that is joining us today is Dr. Catherine Peters. She's a professor, the chair of the Department of Civil and Environmental Engineering, and the director of the undergraduate geological engineering program at Princeton University. Catherine's an expert in environmental chemistry and geochemistry, and will be sharing her expertise in offsetting greenhouse gas emissions with carbon mineralization, capture, utilization, and sequestration. So as you can hear, we have an exciting lineup of experts to hear from today, and we are also extremely excited to be taking your questions. So first, we're going to start with about 10-minute presentations from each of our panelists, and then we will move into questions. But I should say, at any point during these presentations, if you have questions, go ahead and submit them, and we will be going through those when we move into the Q&A portion later today. I also want to give a heads up that about halfway through, we will be taking a 30-minute break. So know that that's in the works too, if you need to go and get a snack or do things like that. So without further ado, we are going to start with our very first exciting presentation, and that will be given to us by Dr. Leslie Shoemaker. So now I'm going to give an introduction of Leslie, and we will be off to our first presentation. So Leslie Shoemaker, appointed president of Tetra Tech in 2019, leads its global operations, strategy, and technical innovation programs. She joined the company in 1991 and has held technical, strategic, and operational responsibilities. She's also served as Chief Sustainability Officer for over a decade, guiding the program to recognize the climate positive impacts of the company's projects while continuing to reduce carbon impacts throughout its operations. She's focused on connecting Tetra Tech's 21,000 high-end scientists, engineers, and technical specialists to develop sustainable solutions by leading with science in water, environment, renewable energy, sustainable infrastructure, and international development. Dr. Shoemaker's technical expertise is in the development of analytics and modeling as decision tools to enhance the environment, especially through watershed modeling systems and optimization of sustainable nature-based solutions. She was part of the Louisville MSD Tetra Tech team that won the 2019 Informs Franz Edelman Award for Operations Research. She led the development of some of the earliest studies on integrated watershed management programs for the US EPA and supported the landmark development of the Basins Modeling System. Her early work on watershed modeling included the development and application of tools for non-point source simulation, such as the Generalized Watershed Loading Function Model. And without further ado, we're going to invite to the stage Dr. Leslie Shoemaker. We'd love to hear your presentation.
All right, thank you, Deanne. And I get to talk about blue-green infrastructure, which is one of my favorite things to talk about, and I'll go through a little bit of a definition for everybody about what blue-green infrastructure is. I'm the water person on the council, so on the panel here. Blue-green infrastructure is one of the ways that we think about nature-based solutions, or solutions that work with nature to manage water. Blue-green infrastructure is at the interface of water and land, and it really builds on some of the early work that was done on low-impact development. In fact, I worked on projects for Prince George's County in the Washington, D.C. area on low-impact development back in the early 90s. And we were looking at how we could mimic the natural environment in an urban area. So how can we actually make something that looks like it's 100% impervious look a little bit more like a natural place? Blue-green infrastructure is often implemented through things like green infrastructure or land-based infiltration areas that capture stormwater runoff and capture some of the toxins and filter them through natural vegetation. But they're really just small patches of land. And when you think about it, how could one small patch of land that infiltrates water from an entire parking lot or a building development be something that actually is going to change the world or address climate change. And one of the things that's interesting about blue-green infrastructure is it's really the sum of its parts. So it's not the one small piece of green land, it's the 10,000 pieces of green land that you put across an entire landscape and its additive impact on water, environment, and the resulting outcome. One good example is it's been adopted quite a bit more in recent years. For example, Los Angeles County, you may have all heard of it, largest, most populous county in the United States, 10 million people. They have about 100 billion gallons of water that actually go into the ocean each year. And the goal is, how can we keep more of that water on the land and infiltrate it into the groundwater? They put a program in place that was actually voted for by the residents called Measure W in 2018. And it actually then dedicates about $300 million a year toward the placement of blue-green infrastructure throughout the entire Los Angeles County area. It has tremendous benefit to all of the communities within the county. It's a very diverse county, as many of you know. It means the placement of blue-green infrastructure in green streets, in parks, in schools, throughout the region as a way to both manage the water and actually have other benefits. LA County is not alone. There are many other places that are now using blue-green infrastructure as a way to manage their stormwater and have other value adds. Places like Vancouver, Canada, Singapore, Melbourne, Australia, many places within the US. Detroit, Michigan has a phenomenal green infrastructure program that actually repurposes land, including abandoned properties, for green infrastructure purposes. And Philadelphia is using it in tandem with gray infrastructure to manage their combined sewer overflows. So this technology of blue-green infrastructure really is maturing. 2 points that I'll go over as sort of part of the engineering view on blue-green infrastructure. One is it's evolving into a multi-benefits analysis. It used to be that we looked at things as more as, you know, working against nature or a monoculture. Now we look at it working with nature with a multi-benefits outcome. So blue-green infrastructure have benefits like heat effects, reducing heat effects in urban areas, improving air quality and by adding more green vegetation, improving quality of life by creating open parks and park environments, improving stormwater quantity control as well as quality control, and adding water recharge, which is really important, obviously, in many of the drought-stricken areas. So this ability to have multi-benefits as part of your decision process for how you treat and manage water is tremendously valuable. But what's engineering's role in actually dealing with blue-green infrastructure? Because when you start talking about multi-benefits, it sounds a little bit more like community planning or master planning or other types of disciplines. The engineering role has been phenomenal in providing the rigor and the quantification of the benefits of these blue-green solutions. Because without being able to quantify them, you can't actually integrate them into a risk mitigation strategy and into a management strategy that's fully quantified and fully managed. And so it's that ability to quantify it that actually creates a whole new way of doing business in the world of blue-green infrastructure. We're creating a body of knowledge that actually allows us to do continuous innovation, balance gray infrastructure or hard engineering approaches with nature-based solutions, and actually quantify the benefits in terms of carbon capture and sequestration, which I think relate well to what you'll hear from the other panelists. But there's also one more piece where engineering is actually adding to the sort of the moonshot aspect of blue-green infrastructure. It's by the use of leveraging of technology for instrumentation and controls, and using it to actually move from static management to active management of blue-green infrastructure. So what that might mean for many of you that don't really follow this every day would mean that now we can have not just a dashboard of where water is being stored across an entire watershed, but now I can have actually a control center for how I manage the water. I can look at what reservoirs are full or what cisterns are full. We can release water in advance of storms so that we can enhance the ability to capture more water to protect from floods. We can optimize how we manage it to improve water quality and react, make sure that we have the maximum benefit for our receiving water bodies. We can quantify the amount of carbon sequestration and track it as we go. And we can even integrate disparate sources of information like crowdsourcing information in how we manage our water systems. And the final part that is actually amazingly important in this side is it's become a way to manage our assets across a region and across a municipality. So in order to actually have these types of systems have their full effect, you actually have to be able to manage the assets and manage the operations and management of them for perpetuity or decades into the future, because this one is the long game, so to speak. So I'm actually seeing many of the municipalities that we work with build much more robust and smart asset management systems that actually integrate it with financial planning, economic analysis, climate change mitigation plans, water management systems, and water quality controls for their overall watershed and their receiving waters. So I see that engineering has a big role to play in actually turning blue-green from an idea and a concept that's been around for quite some time to being actually a practical, on-the-ground, and highly innovative implementation. Climate change today, it's a global challenge, and I see a new way of doing water management as integral to how we actually address it and live with it to the degree that we have to. And with that, I'll turn it back to you, Deanne.
Wonderful. Thank you so much for that. I know I learned quite a bit with the blue-green, and you mentioned the gray engineering technology. So thank you so much for kind of explaining those differentiations and the future of blue-green. Our next topic, the next presentation we're going to have is on infrastructure implications of decarbonization. And that presentation will be given by Dr. Timothy Lewin. I'm going to go ahead and introduce you, and I'm excited to hear that presentation. So, Dr. Timothy Lewin is a Regents Professor at the David S. Lewis Jr. Chair and Executive Director of the Strategic Energy Institute at Georgia Tech, where he manages the university's overall strategy and external relations for its $120 million per year energy portfolio. He's also founder and CTO of Turbine Logic, an analytics firm working in the energy industry, and his work has contributed to numerous commercialized innovations in the energy and aerospace sectors. He's an international authority on clean energy and propulsion and has authored 4 books and over 400 other publications. Current and past board positions include governing advisory boards for Oak Ridge National Lab, Pacific Northwest National Lab, and the National Renewable Energy Lab, appointment by the DOE Secretary to the National Petroleum Council, and board member of the ASME International Gas Turbine Institute. He's also an appointed member of the National Academy's Committee on Accelerating Decarbonization in the United States, Technology, Policy, and Societal Dimensions. His contributions have been recognized by his election as a member of the NAE, a fellow of ASME, APS, and AIAA, and foreign fellow of the Indian National Academy of Engineering. He's won multiple awards, and you can only imagine we're excited to hear from Dr. Timothy Lewin. Take it away, Tim.
All right, thanks, Deanne. So what I want to do is spend the next 10 minutes just talking from basically a 100,000-foot view about infrastructure, and particularly our energy infrastructure and what it looks like today, as well as what it's going to need to look like as well as talk a little bit about the role of engineering. So I have my slides up here on the screen that I'm going to talk through. And in order to start, I'm just going to, kind of a simplified view of our energy infrastructure and our energy system. And by the way, I'm going to largely focus on the US, but my comments here will have relevance to pretty much any developed economy and thinking about how infrastructure needs to evolve. But on the left, that left bucket is basically our energy sources, right? This is renewable energy, it's gas turbine power plants, it's nuclear power plants, and so forth. On the right, the far right, are our energy users. These are cars, these are buildings, these are steel plants, and things like that. And then in the middle is something that we may not think about as much, but yet there's still trillions of dollars of infrastructure. And this is the energy carriers and the way in which we're storing energy. It's a little bit like what's in the middle is a little bit like the plumbing and wiring of your house, right? It's behind the walls, it's in the crawl space, you don't see it, but yet it's really, really important to have those wires moving energy or moving electricity around, or those pipes moving water around. And if you just wanted to take just a very rough cut of what those sectors look like today, roughly just a little bit less than half, about 40% of our energy is moved around via electricity. So there's some source of power, and then it's ultimately moved to the user via electricity. So this is the lights in your house or electric heaters and things like that. And about 60% is via fossil fuels. And now an important thing to recognize about fossil fuels, and I'm going to come back to this when I talk about what we're going to look like if we go to net zero, is that today fossil fuels carry a couple functions. They're the source of energy, which is probably familiar to all of us, but they're also the carrier. They're the way in which we move the energy around, and they're also the storage medium. So there's massive amounts of storage in our energy system just via our gas pipelines and underground salt domes and large oil fields and things like that. Or large oil tankers where we're storing energy. And so all those things are things where we're going to be thinking about evolving. Now, if you want to just put some dollars, there's a lot of trillions being thrown in the air right now with infrastructure bill discussions and things like that. But if you just wanted to get an idea of what's built out today. So this is from a very recent study from a colleague of mine, which is, I have on the bottom here, Dr. Rich Simmons. And if you take out the real estate part of our infrastructure, the replacement value of the US infrastructure is about $37 trillion. And of that electricity chunk, and this includes both the power plants generating electricity as well as all the things that are moving electricity around, is about 13%, just a little under $5 trillion is that replacement cost. And fossil fuels or hydrocarbons, a little bit under a quarter, about $8.5 trillion. So that's what we have that's what we have today. Okay, so what is a potential view of a net zero CO2 system look like? And engineers are scattered all across this picture. And I have the same basic three buckets, except I've added a few things. So on the very bottom, I still have fossil fuels, which might be surprising to some of you, but fossil fuels with carbon capture. And we're actually going to have a dedicated talk a little bit later on this session. So the idea there is that there is certainly going to be some role for fossil fuels. Exactly how much is something part of a larger political discourse that's going on right now, but we're going to have a means of grabbing that carbon that's in those smokestacks or out of the atmosphere and putting it back in the ground. That green arrow is a new one. That is also fuels, but they're not fossil fuels. They're what I would call renewable fuels. So this is things like hydrogen, or sustainable aviation fuels or biofuels, just a whole host of things. But so in other words, rather than using electricity as the means of moving electricity around, of moving energy around, you can just as well use a fuel. And there's no reason whatsoever that it can't be a fuel with essentially a net zero impact on climate. However, a key difference from what we do today, where fossil fuels are both the source and the carrier and the storage medium of energy, is that the source and the carrier of energy are decoupled. So we have some other means, let's say electric power, a wind turbine, a photovoltaic plant or something, and we use that energy. We can not only use it to make electricity, we can also use it to make hydrogen, to split water and make hydrogen or something like that. So what might these sectors actually look like in terms of size? Well, there's lots of studies, there's lots of speculation about what this net zero economy looks like, what this net zero infrastructure looks like. What I have here is one very recent study, which I like a lot, which is just very recently done by Princeton. It's called their 2050 Net Zero America Study. And they did a number of different scenarios, but what I have here, these are some just round numbers for sort of least, if you had to minimize overall aggregate societal cost, what would that system look like? And what you can see is electricity goes up. So we're moving around a lot more of our energy versus electricity. What's also interesting about this is that fossil fuels does not go away. In fact, it stays at about 25%. So roughly a quarter of our energy by that study is still being generated via fossil, but with carbon capture. So this massive new industry, which does not really exist today, of carbon capture. So you can get some idea just around the engineering challenges and just the size of this new industry associated with carbon capture. And then that middle bucket, renewable fuels, is about a quarter. So again, that's just one view, but I think it's a really compelling view, just given the fact that if we wanted to minimize the overall cost. So what's actually going to happen going forward? If I had to put my crystal ball, first of all, I think that between now and 2030, in fact, there's a very recent National Academy study on exactly this. I think the way seems pretty clear. Is that we're going to need to aggressively grow out that left box, the use of renewables in the left box. And we're going to need to dramatically increase the use of electric power as our means of moving electricity, as well as of users that can take that electric power. So for example, transportation. So that's one big piece. But after 2030, there's some significant societal decisions that we have to make as well. And one of those is, what's the role of electricity in moving energy around versus fuels? This picture right here shows it as roughly 50-50. There are some groups out there would like to see much more use of electricity, and to completely move past and put fuels and the use of fuels as energy carriers in the rearview mirror. But exactly what that mix needs to look like is very much something for discussion. The other piece is what those renewable fuels actually look like. There's a word that we sometimes use as drop-in, and what drop-in means is that you can basically take it and it looks indistinguishable from what we use today. That could be gasoline, it could be kerosene, and there's no reason that you can't make a fuel that goes into your car or an airplane that's essentially has net zero CO2 impact, but yet it doesn't really require you to change your car, put in a new airplane engine. That's drop-in. But the cheaper fuels to produce, the cheaper renewable fuels, are things like hydrogen, which would require building out a significant new large-scale infrastructure. So this other significant decision, societal decision, is drop-in or new fuels infrastructure for handling. I guess the last comment I want to make. So this is a picture. If I think about the role of engineering in this, engineers' fingerprints are all over this. But I guess the need for engineers to increasingly be having these large scale, be integrated in much larger societal discussions is absolutely critical. Because at the end of the day, all these things that I put up here, they're technical systems, but they're also techno-social systems, right? There's millions of jobs that are tied up. There's livelihoods that are tied up in these. There's significant equity impacts tied up in these. If we think about what we want to do different going forward relative to in the past, we know that many of these systems have been foisted on some of the most vulnerable members of our society, those with the fewest resources, and we don't want that to happen going forward. If you think about today in the challenges around coal, and just the current political discourse around coal. So coal peaked about 20% of US energy. Today it's down to about 10%. But if you think just how hard that's been for us as a country to absorb that, and then you think about natural gas and oil, which are 3 times the size of that coal economy, about a little more than 60%. So significant thoughts around jobs, where they are, who's getting affected, and things like that. So I think with that, I will stop and conclude.
Awesome. Wonderful, wonderful presentation. And we are going to move on to our next presentation. Thank you so much, Tim. Next, we're going to hear about technologies for a more sustainable future from Dr. Ken Washington. So Ken Washington is Vice President of Software Engineering at Amazon, where he leads a team of engineers developing new consumer devices and services. Before joining Amazon, Dr. Washington was Chief Technology Officer at Ford Motor Company, overseeing the development and implementation of the automaker's technology strategy. His portfolio at Ford included propulsion systems, sustainable and advanced materials. Whenever the screen share goes big, I lose my other notes. So sorry about that little hiccup there. His portfolio at Ford included propulsion systems, sustainable and advanced materials, additive manufacturing, next-gen vehicle architectures, controls, and automated systems. Prior to joining Ford in 2014, Dr. Washington was Lockheed Martin Corporation's first Chief Privacy Officer, Vice President of Lockheed Martin Space Systems Advanced Technology Center, and Vice President and Chief Technology Officer for Lockheed Martin IT. He previously served as the Chief Information Officer for Sandia National Laboratories. In addition to his election to the NAE in 2020, he is the recipient of the 2012 Black Engineer of the Year Award in Research Leadership. Dr. Ken Washington, it's your turn to take the stage.
Thank you, Deanne, and it's great to be with all of you. Today, what I'd like to talk about are things that Amazon is doing to follow through on its commitment for what we call the climate pledge. And I'm also going to talk about a variety of technologies and business strategies that we use to do that. While this applies directly to Amazon, what I really want to start with is the fact that many of the things I'm going to talk about are steps that many other industries are taking and or could take. So please take away from this that these are technologies and business strategies that are available to us to address climate change. And I want to start with the fact that in 2019, Amazon co-founded the Climate Pledge and announced our commitment to achieve net zero carbon emissions across our business by 2040. You're seeing other businesses make similar pledges and commitments. But what does this really mean? What are we really committing to when we say this? The Climate Pledge is all about carbon emissions. The overarching goal is net zero by 2040. Not just by our own business operations, but the full impact of our business, such as shipments and device energy usage. A big part of our emissions is energy consumed by the operations of our products. So putting clean, renewable energy into the grid is a huge way that we can achieve our net zero carbon goal. And I'm going to talk about that. Let's go to the next slide, please. If you look at this value chain, you can see it moves from manufacturing and the materials used to make up our devices to moving those devices to their use to post-use end of life. So when you think about what makes a device sustainable, you have to consider all aspects of this value chain, how it's disposed of when it's no longer used. We want science to guide us. So we conducted life cycle assessments. That's the first key takeaway I'd like for you to have here, is that life cycle assessment technologies apply to understanding this value chain across all of our products. To understand the full carbon footprint is a necessary tool. And when we did this, we were a little surprised by the results. A life cycle assessment it's not a simple process. First, you have to look at the bill of materials for products and their packaging, even doing teardowns to weighing parts and gathering a full spectrum of information. Then we look at the transportation of those products, both from the factory to the fulfillment centers, as well as outbound to customers. Next, we evaluate the use phase emissions. This is the electricity used in the customer's homes to power and charge our devices. And last, we look at the distribution of devices we project to be traded in, recycled, or sent to a landfill. When we went through this process for our portfolio, we found that on average, more than half of our total carbon footprint comes from the electricity our devices use in customers' homes as they're operated. And so what this led us to understand is that this is a huge opportunity for us to make the electric grid renewable. The next biggest impact is emissions generated by the materials and manufacturing process to transform those materials from raw materials into customer products. So these are the two areas where we put our focus. Let's go to the next slide. When we've launched products over the last year with sustainable benefits in these two, so the fact that we're focusing on these two areas means that when we launch our products, and over the last 2 years as we've launched those products, these are the two areas where we emphasize. In terms of energy, we've been busy rolling out low power mode for our new devices, as well as updating older devices via over-the-air updates and technology that are already in customers' homes to have low power mode. Low power mode reduces the device's lifetime energy consumption by using less power during its moments of inactivity. But this isn't enough. In order to go further, we had to introduce a new strategy. And I'm really excited by the fact that Amazon was the first electronics manufacturer to commit to addressing the electricity used by our devices by putting renewable energy development onto the power grid, starting with our Echo devices. And just last week, we announced that we're making investments in additional wind and solar farm capacity, such that by 2025, we will produce enough clean energy equivalent to match the use of all Fire TV Ring devices and now also all of our Echo devices. Taking all these together, we expect this will produce more than 5 million megawatt hours of clean energy per year. That's enough to power more than 400,000 homes every year. So we've made great progress in incorporating also renewable materials into our products, addressing the other part of our priority, and we've reduced waste in our packaging. Over the last year, we've eliminated an estimated more than 29 million plastic bags from our devices and accessories packaging, and the packaging that's shipped from our suppliers. And this is compared to the same period in the prior year. And we always like to remind people that you can also trade in and recycle through our trade-in and recycling programs. This is where customers can give use to their devices a second life, as opposed to having them go to a landfill or be recycled at lower efficiency when they're done using them. So we've made some really exciting progress. Let's go to the next page, please. So I've talked about a lot of ways that you can track and then address renewable energy and sustainability through devices and services. But I want to end on the fact that there's another way, which is to raise consumer awareness about the products they buy in the first place. This is what we call our Climate Pledge Friendly program. For any product category sold on Amazon.com, we're now badging products that have achieved one of a select set of sustainability certifications. This includes our own devices. This makes it easier for customers to identify and shop for products that match their values. But we didn't just stop at badging. We really want customers to understand what we did by being highly transparent. These attributes are designed into each product, but they're a little different. So we highlight low power mode or energy, provide them with an energy dashboard. So you'll see this block on our devices detail page when you're shopping online on Amazon.com, in addition to the Climate Pledge Friendly program. So let me end there by just summarizing that everything I just spoke about are things that Amazon is doing, but there are also things that other companies could do, and there are things that are impacting other companies because they sell their products on our platform. So let me end there, and I hope that you've taken away from this the fact that there are many things that technology can do to help us address climate change, from the front end all the way through the full life cycle of the product's use and its disposal. Thank you.
Awesome. Thank you so much for that presentation. It's really interesting to hear you identify electricity as a focus, and then Tim hark on that as a need for us to really focus on going forward. We have another wonderful presentation in store. The next presentation is going to be on the role of distributed power systems in a quest for climate change. And I'm going to give you a brief introduction to Dr. Mohammad Shahidapur. Mohammad Shahidapur is University Distinguished Professor, Bodine Chair Professor of Electrical and Computer Engineering, and Director of the Robert W. Galvin Center for Electricity Innovation at the Illinois Institute of Technology. He has 45 years of experience with electrical power system operation and planning, and his sponsored project on perfect power systems has converted the entire IIT campus to an islandable microgrid. For his contributions, Dr. Shahidapur has received the IEEE Burke Hayes Award for his research on hydrokinetics, IEEE Power and Energy Society Outstanding Power Energy Educator Award, IEEE PES Ramakumar Family Renewable Energy Excellence Award, and several other awards. In addition to his election to the NAE, he is a fellow of IEEE, the American Association for the Advancement of Science, and the National Academy of Inventors. He's co-authored 6 books and 800 technical papers on electrical power system operation and planning, and was the founding editor-in-chief of IEEE Transactions on Smart Grid. Mohammad, it's your turn to take the stage.
Thank you very much, Diane. This is a picture of Chicago skyline. I've taken this from my office. It was actually taken yesterday. It shows the sort of footprint of a microgrid that we have at the university. So I'm going to discuss that and then sort of show how this idea is going to help fight the global change. So, of course, the rest of the world may not look as beautiful as you saw in that photo. We're dealing with issues like fire in California, hurricane in the south, tornado, flood, earthquake, and a whole host of other extreme events that have come around because of global warming. In fact, the climate change has increased both the frequency and the severity of adverse weather throughout the world. It's interesting to know that there have been 10 times more massive power blackouts each year in the 2000s as compared to those reported each year in the 80s and 90s. And just in the United States in 2018, we had something like 6 severe storm extreme events that each one of them incurred the economic losses of over $1 billion. So it's something to really consider as to where we're going and how we're going to battle this subject. One of the reasons for these sort of issues that we see coming around is the fact that our communities are getting more urbanized, in the sense that if you look at that slide, in 1950, about 30% of the global population lived in big cities. It's expected that by 2050, that number is going to increase to 70%. 70% of the global population is going to live in big cities. For a number of reasons, big cities are more secure, there are more jobs available, and that sort of growth is in particular in developing countries. And you can see what has come with that. Issues with transportation, with water, clean water, air. In fact, I took this photo a couple of years ago. There's a big city behind this. I mean, that's all you can see, a tower. And you can see what we as human beings have done to this, globe. And also, this is a photo that was taken last year in China. This is in January 2020. You can see the Beijing and the sort of NO2 density. And then this is a month later. Same place. We can see that when they shut down the stores and everybody stayed home and nobody was driving cars, what happened to the city? What happened to this, massively populated Beijing? How we cleaned it when we eliminate those gasoline cars, when we sort of shut down places where they were using so much of fossil fuel. And what has been the solution? We have sort of resorted to a lot of renewable energy throughout the world. So electricity grid sort of is undergoing profound changes with the increased use of renewable energy. So, but that comes with its own problems. Like this is, I've seen most of you, I presume most of you have seen this. This is a sort of a dot curve in California that shows how the use of energy and the sort of thermal energy production changes throughout the day as we increase the solar energy usage. So during the day, when we have lots of solar available, the use of thermal energy drops. But at night, when the sun is not shining, we resort back to the use of thermal energy. And the problem is that the electric power system is not accustomed to this kind of changes. These massive ramps that we have to come up with in order to increase and decrease the thermal power generation is not something that the electric power system can do and operators can do. So what do? We go to smart grid automation, information technology, and in particular, the use of distributed control of load. Use of smart dishwashers and washing machines and EVs and all that, which is going to have a major impact on this sort of the use of smart grid. So what we do here is take, this massive peak of energy use at night that creates such a significant peak, and move it around, move it to areas, like to the left, move it to midday or very early hours so that we can eliminate that. And we can do that by the use of smart grid and automation, where we sort of eliminate the usage of electricity at peak hours by shifting the use of charging cars or washers and dryers and all that to after midnight. If you move it to this area where the usage of electricity is much less, or even here, you can eliminate this peak. So this the use of smart grid and automation, and as I said, information technology has to come around with the usage of renewable energy in order to make that possible. So where do we go with that? The use of microgrid, like as I pointed out earlier, and as Leanne pointed out, we've converted the campus to a perfect power microgrid. So we are not the first one who built this. In fact, the person who built the first microgrid was Edison. So Edison built the first microgrid back in 1881 in New York area. And there were two distinct features that his microgrid had. One was that it was an islanded system because, there were no grid those days. So he built this system, started pulling wires to neighbors who were mostly rich people, could afford electricity those days, and start, charging them. And then it took us, a few decades to realize how valuable this commodity is. And that's what we built this massive electric power system that you're using. The other thing that Edison did was that, Edison was a DC guy. So he built a DC system. So this system that Edison built was a DC. So interestingly, we're going back to the days of Edison. We're building a lot of DC systems. In fact, this is in Virgin Island, one of the projects that I participated. So all the renewable energy in the form of PV, those are DC generation. And also you have a lot of DC loads, your phone, your cell phone, your laptop, all the LED lights, those are DC loads. So you're generating DC, you're using DC loads, so why don't we just use a DC grid? So as I said, the use of islanded system and the use of DC is coming back. So basically the difference between what we do now and what Edison did is significant and ongoing innovations in energy efficiency, renewable energy, battery storage, power monitoring and control that have resulted in a diverse array of advanced technologies in smart grid. So we are doing it with smart technologies, wireless systems in order to serve our customers all over. One example of this microgrid is the university system where I come from. We have converted the whole campus to a microgrid. So it's a 12 megawatt system that we can island it. We save university about $1 million annually. So what we're talking about basically is to build a grid of the grid. So when we convert the third largest city in the country, Chicago, to sort of a grid of the grids, lots of microgrids, we can come up with sort of a smart solution, smart cities, which allows the electrification of not only the remote areas, but also metropolitan communities. These microgrids enhance sustainability, reliability, resilience, security, and economics of electric power system. As an example, after we built this at the university, we are working with the local utility company to build the second microgrid. So now these two microgrids are interconnected. This is the universities, and this is the Bronzeville, which is next to the university's community. And these two microgrids can talk to each other. And in case of an emergency, they can save energy. So I think the future of electric power system, I think the future of our communities belong to these distributed power control systems, where we can promote a lot of renewable energy, a lot of storage, and in particular, we can control the load to the extent that, as I said, we can enhance all of these: sustainability, reliability, resilience, security, and economics. In doing all of that, what we need to remember is that the socioeconomics and socio-political aspects of these things are extremely important. And we as engineers have overlooked them. Issues like policies and who's going to pay for all of this, and how we make individual customers to participate in getting all of this done is something that I hope the National Academy can participate and come up with a solution to all of this. Thank you very much.
Thank you so much, Mohammad. Really, really interesting stuff. And we have one more presentation for the first part of our forum, and that's going to be from Catherine Peters, Dr. Catherine Peters. She'll be speaking about offsetting greenhouse gas emissions with carbon mineralization, capture, utilization, and sequestration. So Dr. Catherine Peters is the George J. McGee Professor of Geosciences and Geological Engineering, the Chair of the Department of Civil and Environmental Engineering, and Director of the Undergraduate Geological Engineering Program at Princeton University. Since 2017, she has led her department through transformative growth with key faculty hires, multidisciplinary research collaborations, and educational initiatives on the water-climate nexus, future cities, robotics for advanced mechanics, and environmental biotechnology. She teaches courses in environmental chemistry, engineering, energy and the environment, and sustainable design. Dr. Peters is an expert in environmental chemistry and geochemistry, known for her leadership in sustainable energy technologies, with a focus on geochemical strategies for greenhouse gas mitigation. She's given numerous invited seminars and published more than 100 peer-reviewed journal papers, which have been cited more than 5,000 times. She's a fellow of the Association of Environmental Engineering and Science Professors and served as president in 2002. In 2020, she was honored with honorary board certification by Eminence in AEES and received a Distinguished Alumni Award at CEE at Carnegie Mellon University. She's editor-in-chief of Environmental Engineering Science and has served on numerous advisory panels for the U.S. Department of Energy, including the stakeholder group for the National Risk Assessment Program. Catherine, we're excited to hear your presentation. Take it away.
Thank you very much, Deanne, for that introduction. Okay, it is widely agreed that to achieve the massive decarbonization that's needed between now and the middle of the century, that greenhouse gas emissions will need to be offset with negative emissions technologies. And negative emissions technologies remove carbon from point sources and from the atmosphere and utilize or sequester that carbon. Many roadmap analyses say that negative emissions technologies will play as significant a role as any of the low carbon technologies we're talking about in decarbonization. And it's estimated that by 2050, negative emissions technologies can account for as much as 10 gigatons per year of CO2 of negative emissions. So today what I'm going to do in this presentation is I'll share with you some very promising strategies of negative emissions technologies. While I've been talking, I bet you've been looking at this beautiful nano XCT image. This is an example of carbon mineralization and carbon utilization that we've been developing in my lab, and I have a slide on this to explain it further. Next slide, please. Okay, this slide is about carbon capture. Carbon capture is the term we use to describe taking CO2 out of a gas phase, either from a very concentrated gas phase like a power plant or directly from the air. To give an example, last week the company Climeworks announced the opening of the world's largest direct air capture plant. It's in Iceland, and that project is named Orca. Carbon capture is an old technology. It's historically been done with liquid amine solutions. It's technology nearly 100 years old, but today many researchers are examining solid sorbents, which are far more efficient than amine solutions in terms of the energy needed to recover the CO2 and regenerate the sorbent. On this slide, I'm highlighting the very promising research of my colleague at Princeton, Professor Claire White. She and her team are developing layered double hydroxides, which have tunable selectivity to absorb CO2. And these materials have a good balance of low cost, high absorption capacity, and moderate energy needs for regeneration. Next slide, please. Okay, this slide is about carbon mineralization. So one of the negative emissions strategies is carbon mineralization, which has also been called mineral carbonation. In carbon mineralization, CO2 reacts with metals and metal oxides to form thermodynamically stable carbonate minerals. The materials needed for these reactions are alkaline materials, and fortunately, waste streams from existing industries can provide these alkaline materials. It's estimated that the collective waste streams from global industries can provide 7 billion tons of alkaline materials needed for this. For coal ash alone in the United States, it's been estimated that between 40 and 200 million tons of CO2 per year could be captured globally. So in the research in my lab, we are examining these reactions in a kill two birds with one stone strategy. We're examining carbon mineralization processes in terms of their potential to solve another environmental problem, which is heavy metal pollution, such as arsenic, copper, cadmium. Carbonate minerals have the potential to co-precipitate trace metals. And so this image is a synchrotron-based nano X-ray tomography image of a spherical crystal of calcium carbonate with another precipitated phase of zinc carbonate. This is evidence of carbon mineralization and carbon utilization, because the carbon is being used as an environmental remediation process while it's also being sequestered. Next slide, please. Okay, this slide is about geologic carbon sequestration. After CO2 is captured, it can be injected deep underground, such as 1 kilometer or more, where it can be permanently sequestered. An example is the Sleipner project, which is run by Statoil, that is injecting 1 million tons of CO2 per year under the North Sea. This has been going on since 1996. Another example is the CarbFix project in Iceland, in which CO2 is injected into basaltic rock. Studying geologic carbon sequestration has been a cornerstone of my research for nearly 20 years. And the research question that really motivated me was, will it leak? Will it leak out of where you put it? So when I started this research, I thought about the enormous geochemical perturbation that would come from introducing vast quantities of CO2 underground. And I wondered whether the acid would erode the overlying cap rocks and enable the CO2 to leak from where it was injected. So my students and I looked at this from all angles, nearly 20 years, and many papers and many PhD students later. I have concluded that it is highly unlikely for CO2 to leak. There are numerous trapping mechanisms, even ones that we didn't expect. And so in my opinion, geologic carbon sequestration is a technology that is ready to go, and what is needed is a stream of captured carbon for injection. Last slide is my next slide, please. Okay, so on this slide, I feature the research of Professor Jeff Balicki at Ohio State. In his work, he and his colleagues are studying CO2 utilization in the context of subsurface energy storage. There are many approaches to subsurface energy storage. We're all well aware of the well-established procedure of seasonal underground storage of natural gas, but also energy can be stored as heat in the formation, heat in the carrier fluid, as well as mechanical energy. We call that PV work for stored fluids that are compressible, like CO2. In Dr. Balicki's work, they have compared CO2 cushion gas as an energy storage technology, and they have determined that subsurface energy storage has enormous capacity and energy discharge potential, as shown in this graphic. So this technology is an example of simultaneous carbon sequestration and utilization, in which the sequestered CO2 is being utilized for subsurface energy storage. I will conclude by saying that all my examples come from researchers in civil and environmental engineering. And from my vantage point as a chair of a civil and environmental engineering department, I believe that engineers in this field are well positioned to lead technological advancements in decarbonization and negative emissions strategies. So this concludes my formal remarks, and I look forward to some questions and discussion.
Wonderful. Thank you so much for that presentation. And thank you everyone for your wonderful presentations to kind of kick things off. We are about to transition into a Q&A. We're going to do Q&A for about 15 minutes, and then we'll be taking our break. You guys ready? All right. We already have questions coming in from the audience, and one of them actually is a question that I had kind of teed up to ask. So when we think about climate change, right, there's prevention, there's mitigation, but then there's the other side of the equation, which is, adaptation to everything that's going on. I know here in California, right, some of us feel like forest fires are like the new normal. I just wanted to talk about sort of the balance of that in engineering. Do we focus on one more than the other, or both? Leslie, I was thinking you could talk about that. One of our questions that came in also had a specificity about blue-green and the role of reducing climate change or adapting to climate change.
Yeah, I thought adaptation is such an interesting, I read somewhere recently where it said that even if we did everything to mitigate climate change today, we'd still be living with 30 years of wild weather, so to speak. And so adaptation is got to be, from my perspective, a big part of what we do. And a lot of what I talked about in terms of nature-based solutions are really focused on that combination of doing things that help us adapt, but at the same time also reducing the carbon footprint of our cities and urban areas. The wildfires, I think, are also a really relevant point for this year. California has burned just about 2.5 million acres already. And the thing that is probably the most profound in many ways is that the air quality impacts associated with those fires affected the entire United States, including all the way to New York City. And that means that many of the adaptations that we need to make for climate change are not isolated. They're not in just one location. They are broad regions of the country. They are very difficult to control locally. And air quality is, of course, a profound example. You could live in the most pristine part of the United States and still have an air quality problem. And that's a eye-opening, I'd say, for all of us.
Thanks for that. Yeah, so in terms of thinking about looking forward, Tim, I know you talked about sort of in the future what our energy consumption needs to look like to kind of balance things out. We had a question here about, in the Princeton 2050 decarbonization model, what are the zero carbon energy sources that generate electricity? Do you want to tackle that question?
Sure, yeah. So I mean, I think basically the big two, so today in the US, the largest source of net zero is hydropower, so dams. We're probably not building a whole lot of big new dams, but the most rapidly growing sources are wind, number one, and solar photovoltaics, number two. Those are really the big two. And in fact, I think last year, I mean, wind is not alternative energy anymore. Last year, wind produced somewhere around 15% of US electric power. And there are days in Texas where it was generating more than half their electricity.
And just a follow-on question to that, like when you look to the future, when you think 20 years from now, when you think about the infrastructure of these new energy sources, do you see homes all with solar panels? Do you see wind farms everywhere? How do you see this kind of affecting? Where do you see like a lot of this growth in terms of infrastructure?
Yeah, and let me just, if I can just add one thing to my last question, I missed a big one, which is nuclear, and so I think and that's the one that is most tied up to to a lot of political and regulatory issues, but nuclear also potentially can play a significant role. You know, the question of sort of just very large scale concentrated power plants like we have today versus this very distributed, even to the level of a single rooftop. I'll just say there's a lot of different visions out there, and to put it nicely. And I think, frankly, I think the mix is it's going to be a mix. Is that there will continue? We are today building large scale PV sites. In fact, the Southeast where I live, the state of Georgia, is a national leader in solar, but a national leader in large scale distributed solar, whereas other states, you know, have much more significant build out of rooftop. And so you're going to see a whole spectrum ranging from large scale wind and solar plants all the way towards much smaller scale. And I mean, there's a lot of issues tied up there around jobs, around equity, and views, you know, in addition to energy costs, just based upon what local community benefits are.
And you brought up a great, go ahead. Yeah, Ken.
If I could jump in, I wanted to add to that because I think it's important to acknowledge that economics play a huge role here. And technology plays a big is a big factor in driving down the cost of renewable energy. And we've seen huge movements in the drop in costs for solar energy, solar cells, and more innovation is continuing in that space, as well as a huge drop in electric battery technology costs. And as we see these prices come down, it lowers the barrier of entry and of various industries to actually advance the technologies into consumers' hands. That's why we've hit an inflection point of battery electric vehicles, for example, in the automotive sector. You know, I'm not speaking about automotive anymore. I'm no longer in that sector, but I'm aware that inflection point is upon us. And you're seeing that same inflection point happening with solar energy in the distributed power grid as well. And I expect that to continue as technology continues to advance in advanced materials and on other fronts.
I think that's a really good point. And I mean, at the end of the day, the bottom dollar matters, and creating equitable, you know, access in terms of lowering cost is one aspect of it. But I think we all know here that climate change it doesn't impact people the same way, right? It's definitely not equitable in the impact. And we have some questions here about climate equity. Yeah, Mohammad, did you have a question on that last one, or do you want to take my next question?
I can do both, but let me just comment on the last issue, and that is, we talk a lot about building more resources, additional solar PV, more nuclear, hopefully getting rid of all the coal plants. But I think the element that's going to play the most profound effect is going to be playing with the load. In a sense, control of the load, reducing the load, rather than keep increasing the load and building more infrastructure, more generation, more transmission. I think the future, in particular when we talk about smart grid, depends on or relies on reducing the load, in the sense that levelizing the load, because a lot of people use electricity during the peak hours, and then after midnight, nobody is using electricity. It's the same thing with our transportation. We keep building more highways as population goes up because people are buying more cars. And then you look at the same highways, 2 o'clock in the morning, there's nobody on the road. Yet the government has to maintain those roads. You know, they have to change the, pavement and all that. The solution is to levelizing the load, reducing the peak so that we don't have to build so much infrastructure, and then managing it to the extent that we teach people to use electricity, more intelligently, and that's going to happen by smart grid. So I think the future is going to depend a lot on how we control the load, how we socialize this issue, and how we teach our customers to use electricity more intelligently.
So to follow on to that, and you're talking about levelizing load, I mean, I think you mentioned there's the technology aspects of that, but also just individual habits in their consumption, right? So are you suggesting that we need to better educate folks about their energy consumption and we've seen examples, right? The power grid in Texas, they had to go in and actually shut off power, and it wasn't advice, it was mandated, right? So where do you see that going in the future? Just more education in terms of that, or technology playing a role to level that load?
I think both. I think education in particular, I mean, I'm in the education business, but I think education is going to play such a major issue in sort of bringing customers into perspective, because without customer participation, we cannot get the issue done. If you're talking about control of the load, we need the customers to buy into that. So education is going to play a significant role. Like in Illinois, you know, I live in one of the suburbs. When they were going to roll in these smart meters, there were neighbors who didn't want these smart meters. They were saying that, oh, government wants to install these meters so that they know what we're doing in our living room. And, you know, I said, well, as long as your cell phone is on, they can figure out what you're doing. They don't need the smart meters. So I think the education of customers, to the extent that they realize why we need these new technologies and why we need to levelize the load and why do we have to use energy and electricity, you know, more reasonably, it's going to be such a critical issue. I think we have a long way to go, but the sooner we start, the better we're going to be.
I think I'd be a little careful about putting too much hope on that. I mean, I think it's important. I agree with you, Mohammed, that we need to address education. But people do things that are easy, right? I mean, they just don't want friction in their lives. And so I think we as engineers and technologists have to step up and make it easy for people to do the right thing when it comes to sustainability, which is why we do the badging program on the Amazon.com website. Make it easy to pick low cost, low energy devices. So we have to do a better job of making energy efficient or delayed energy use devices easy to use, so that they're, you know, it doesn't require you to do all these extra steps to delay the use of your dishwasher at night. I mean, how many people actually know how to program all their smart energy devices in their homes so that it uses energy in the low energy peak time periods? Most people don't, right? Even when you buy a battery electric vehicle, you're going to plug it in, and who's going to go through the effort of actually programming it so it charges during the times when the energy is low? Unless that's automatic, a large fraction of people aren't going to do it. So I think technology has got to play a huge role here in making it easy to do the right thing when it comes to level loading of energy in the low usage times and low cost times.
That's why I use the word smart grid. That's why I use automation in my presentation. Once you set up these technologies, you don't need as much intervention of the customer. However, the customers would have to buy into that. I mean, you guys make all these devices, Alexa, people have to buy that. I mean, Alexa won't come into the house. The customer have to realize and believe that those technologies are going to help the future.
Right on.
You can tell it's getting good. And I saw Tim had his hand up. We're going to do one more response to this, and then we're going to take our break. But it's getting good. We got lots more Q&A after this. So go ahead, Tim.
Yeah, well, I think just to, the question we started with was the equity question, which I think also is a really, really good point, because, as engineers, sometimes we're used to thinking about what do we do to minimize sort of overall societal cost or sort of overall emissions. But, what this equity discussion is really highlighting is we have to also sort of get a little bit more fine-grained and really understand the impacts and how they're distributed. And so the same life cycle analysis tools that Ken talked about, these are the things that we can bring fully to bear to understand the costs and how these costs are borne and distributed across all income levels, or the jobs impact, or the air quality impact, or the climate impacts of rising sea levels or urban heat islands.
Really good stuff all around. And I think we're going to, when we come back from the break, we're going to keep digging in on climate equity and talk about that and many, many other topics. So at this point, we are going to take a 30-minute break, and we will be back here at 12:45 Pacific time, which is 3:45 Eastern time, and we'll continue taking your questions. So thank you so much, everyone, for participating so far, and we look forward to taking many more questions. Welcome back, everyone. Welcome back to the National Academy of Engineering's Forum on Engineering Responses to Climate Change. I hope you had a wonderful break, and we are ready to dig into all kinds of questions. So we still have some questions that have come in previously that we're going to tackle first, but feel free to submit your questions, and we're going to address as many of them as we can for the rest of this session. So we're going to kick things off with a question for Leslie. We have a question here about climate equity issues underlying these timely conversations. And an example was given here about Manhattan. Manhattan can build flood barriers with sea level rise, but that leaves Bangladesh disproportionately vulnerable. How should engineering adapt to address these global north versus south issues? And I know you're passionate about water and there's ecosystems and talking about flooding as well. So I'll give that over to you, Leslie.
Yep. Yeah, sea level rise, dry weather, flooding. We've got some areas in the US and many parts of the world that are actually starting to get flooding whenever there's a high tide even, or there's a full moon. And then others that are impacted by hurricanes. And clearly there are parts of the world, not just Manhattan, but others where they can do hard engineering that will help to a point. Not necessarily for any catastrophic event, but can help. There's a long lead time to put those projects together and actually construct them, just like what was done post-Katrina in New Orleans, which that flood protection structure actually did prevent some of the impacts, but not all, of Hurricane Ida just recently. And but one of the challenges will be for many of these areas, a hard engineering solution won't be there. There's some types of adaptation that can help, some of the natural solutions, some of the flood barriers through wetlands and other techniques, the sort of the green-gray solutions can help, or at least allow communities to respond quickly when something does happen and recover faster. But I'd actually like to broaden it a little bit, Deanne, because I think one of the biggest issues really is this a little bit of change in temperature has huge effects on agriculturally linked economies. So we work with many development agencies around the world, and there are many, many countries where just a slight change in temperature is changing the crops that they can grow. And the adaptation will be searching for new crops, new economies, different ways of coping, and also dealing with extreme high temperatures, which make it very difficult for those that need to work in the outdoors and can't afford air conditioning 24/7 to adapt to those conditions. So I think there's many angles here where we'll be looking to see how we can help communities at large help to adapt to these changes and live through them.
Great, fascinating stuff. We have another question here for Catherine. And it's really going back to CO2 sequestration and leakage. There's a question here about, did you account for reservoirs that had been extensively drilled for oil and natural gas? But I'm also going to throw in there, I mean, I think everyone's heard about, the melting ice and the potential for methane to seep out and leak. So I'd love for you to just tackle that in terms of all these different leak sources.
Okay, Deanne, thank you. I'm going to handle those two things separately because they're really separate issues. First, about injecting CO2 into a formation that might leak, because we have on this earth more than 100 years of searching for oil, and so most underground reservoirs are explored in some way, and so that has been considered as a possible source of risk. Modern petroleum engineering practices are good in terms of good practices for abandoning wells, shuttering wells, but old practices from years ago are less good. So there is a possibility that there are formations that are perforated that could be leaky. The strategy would be that leakiness can be assessed before an injection project would begin. It's all about pressure. Leakiness is related to pressure, and if you can pressurize a formation, it can hold the pressure, then you can determine that it's not leaky. And once the pressure has dissipated over time, then the leakiness risk is reduced. So the strategy is to avoid formations that would have been determined to be highly perforated and leaky. But the other thing I want to point out is that CO2, unlike methane or natural gas, CO2 is highly soluble in water. And that is one of the reasons it remains trapped, unlike natural gas, for example. If it's injected deep underground, even if it does leak from the target formation that it was injected into, it would encounter so much water along the way that it is highly unlikely to make its way all the way to the land surface and be a leak at the land surface. So yes, we have looked at this. I have some papers on that as well as a lot of others. And so it's a good point. I'm glad you brought that up. About methane. Methane, as I said, we do store natural gas underground. There are problems with leaks, and methane is a very important molecule because molecule per molecule is 25 times more potent as a greenhouse gas than CO2. So even though there's less of it, it's still a very important greenhouse gas. And I think right now there needs to be better strategies, technologies, and mandates for measuring methane releases from all sorts of sources, from oil and gas operations, as well as from agricultural sources, as well as from landfill gases. These are some of the big sources of methane, but we don't really have good inventories. We need much better ways to measure that, as well as mandates for monitoring.
Good stuff. So you mentioned the need for measuring, the need for monitoring. This is a question, obviously, that I think it just is at the heart of engineering, which is using more and more analytics to do more and more research to better predict these things, to better monitor these things. And I know all of you have touched on these different roles. I'm actually going to go to one of the questions we have, which is about, Ken, can you speak about the relationship between customized grids and energy efficiency? Mohammad, I know you've talked about smart grids. Tim, Leslie, I know you've talked about analytics. I'd love for us all to kind of go down the line and chat about the importance of analytics, AI, machine learning, and the engineering response to climate change. So go ahead, Ken.
Sure, I'll start. So let me start by just giving a nod to the fact that artificial intelligence is rushing into our lives at an amazing rate. I mean, you're just seeing devices that you don't even know they have AI in them, that do have AI in them. And if they don't have the AI in the device itself, the device is connected to the cloud, and it's pulling on AI and analytics in the cloud. So AI is growing at a breakneck pace, which means that the energy that AI computer chips consume is also growing at a very rapid pace. So what we need to recognize, and the engineering community has a role to play here, is in engineering the compute architecture and the compute fabric to power these increasingly capable, increasingly power intensive applications with the right types of processors and the right types of computational architectures. And so there's a lot of activity underway in fact, you can see that if you just do a Google of startups that are working in the custom chip space. It's now a very active space of technology development to design and develop custom AI chips to support the AI fabric that's growing, so that you've got the right computational architecture for the right computational job. We're not there yet. There's a lot of room for more innovation and a lot more technology development. And Amazon is certainly working in that space very aggressively because we have very large data centers, and we're putting the right types of computational architectures in those data centers to be as computationally and energy efficient as possible. But we're doing the same thing in our devices as well. And those devices will continue to evolve and develop to be more more sophisticated and more energy efficient. So AI is here to stay, and it's only going to grow in energy in demand because it's making people's lives better, and it's making everything that we do more efficient and more enjoyable. And so I don't think the answer is tapering down the use of AI. I think the answer is designing the AI and the architecture underneath that to be more efficient and more effective.
All right, on that same topic, let's go to Mohammad and then Tim.
Well, I talked about levelizing load, and that's basically impossible to implement without using automation. And these computational technologies play a significant role in computation. So as Ken pointed out, the use of AI is something that's just starting. And primarily the reason we are so interested in that subject and the interest is growing is because we got so much data to play that. So AI help us delve into that and find out what's the best sort of type of data we need to use in order to get the job done. So yes, I think AI is just going to grow and grow and grow, and it's going to help guide customer choices and how we're going to manage the energy usage in the future.
All right, and then Tim.
Yeah, I think another way to put a completely different angle on AI, particularly around energy, is that in many cases, you know, if we're looking at these engineered systems, these are physical systems, they obey physical laws. And really what machine learning and AI does a lot of is it tries to learn and better understand the nature of the system from the data that it's producing. So we call that data, and I like to call them data-driven approaches. But there's a lot of innovation, a lot of companies that are working sort of at that intersection of expertise and just knowledge of how a power plant works or how a grid works and the actual underlying physical laws, and using data-driven approaches, AI, bringing those together. So I'm as you mentioned in your intro, I'm the founder and CTO of a company called Logic, and we do exactly this on solar farms and gas-fired power plants. And there are significant applications in monitoring and diagnostics to make the grid more resilient, really bringing those two together, but also reducing the energy efficiency. You know, it's probably an $80 billion market per year, simply using better analytics to operate what we have more efficiently.
Hey, Deanna, can I have a go back before we move on to the next
You
one?
can have a go back. Go for it, Ken.
I would love to have a go back because, I mean, what I talked about and what Tim and Mohammad talked about is really the present. And I think we've got to think about the future too, because if you kind of wind the clock back 5 years ago, what were we thinking about that what 2021 was going to look like? I mean, how accurate was our prediction? And it was probably pretty bad. Right. And so technology is going to accelerate to the point 5 years from now where we won't recognize the pace of innovation and the pace of energy consumption and the pace and the scale of AI use and the implication that has for sustainability and energy consumption. And so as I look 5 years in the future, one of the things I'm personally working on that I didn't have in my bio because it wasn't public at the time, but now it is I'm working on consumer robotics. If you look 5 years into the future, do you imagine that every home and every business will have at least one robot? And I think the answer to that is yes, which is why we're working on consumer robotics and other robotic technologies. That's just one glimpse into that 5-year future. So if everyone has one or more robots in their workplace and in their home, imagine how those autonomous things, those robots, could be helping you make better choices when it comes to sustainability and what kind of power they'd be using, how the AI would help you make better and smarter choices and decisions. My point is we need to not just think about today, but 5 to 10 years from now and how technology will shape what our lives will look like and sustainability and energy consumption uses implications of that.
I think it's a really good point. I know, Tim, you brought up earlier in your presentation, infrastructure related to, some of these alternate energy sources like hydrogen, right? Just the infrastructure that would need to be created for that. But we have a question here about drop-in fuels. So thinking about like the future, how can we progress to the future have these new fuels, but use our existing infrastructure, right? So can you shed some light? I'm going to give you this specific question here. Drop-in fuels rely on a source of carbon, which is finite if it originates from biomass. Do you have an estimate of the percentage of final energy that can be obtained with drop-in fuels? Should these drop-in fuels be used only for air transportation, or is there enough biomass to fuel ground and sea mobility?
Yeah, thanks, Deanne. So I think let me just first remind everyone what we mean by drop-in fuels is that, today our economy today is basically built on natural gas, which is methane or kerosene or diesel for trucks or jet fuel for cars. And I mean, those are just simple different configurations of carbon and hydrogen atoms. There's lots of other potential ways you can configure these things to make fuels that burn. Those just happen to be the fuels that our society is based on because there's a lot of them naturally. And so when we talk about a drop-in fuel, what we mean is something that looks like those. And so you don't have to get a new car. If you were to make that kind of fuel, you wouldn't have to get a new car. You wouldn't have to get a new jet engine. You wouldn't have to get a new gas-fired power plant. Those are just examples. So, so that's the whole idea of what we're trying when we're talking about drop-in fuels. In contrast, other things that we're talking about, like ammonia, which is NH3, people are talking about using that as a hydrogen carrier. There's obviously a big farm ag sector that uses ammonia for fertilizer and things, but it's just not a common thing. You can't put it in your car, et cetera. So that'd be an example of a non-drop-in fuel. So just a quick, what we mean by that. So then the question is there enough stuff to natural sources to actually replace the fuels that we have today, drop in? And so if you're only using, and by the way, there's really two ways you can make it. One is biological, the other is use chemistry. And there is certainly not enough natural biological stuff to replace the massive amount of fuel that we use today. I mean, today most landfills today we pull methane off those today. It's a commercial, you can make money doing that. There's some farms out there, they recycle the manure and they turn it, it's almost like magic. You turn it into diesel. The stuff goes into this big hole in the ground and out comes power. But that can't scale. Although we can certainly scale it up. On the other hand, the chemical route, where you basically take, again, what is fuel? It's basically a carbon and a hydrogen atom. So the carbon, if you take CO2, you can take it out of the air, you can take it from a power plant exhaust. The H, you can take that from water. If you have a renewable energy source that you can use to make that happen, you can synthetically make the fuel. And that's virtually, that could certainly scale. It's just today it's much more expensive than the gasoline you buy at the pump.
It all gets interwoven. We've talked about bottom dollar. We've talked about the AI and robotics, and then we all started with Leslie talking about how we can learn from nature as well. And so some of these topics I think we're all talking about is how do all these things fit together, right? So I have a question here about transmission capacity. So we're going to kind of change gears here a bit and talk about transmission capacity to move electricity from where solar and wind sources are located to where the energy is needed. How do microgrids fit into this picture? And I thought this would be appropriate for Mohammad. You want to chat about that?
Of course. Well, you cannot put all your eggs into one basket. In a sense, you need a holistic solution. We need to look into very large solar farms as well as the solar panels that we can place on individual roofs, the roof of individual houses. So we need both. But the point here is that we don't need as much transmission as we did in the past, because previously we built very large generating plants that have to be placed very far from residential areas. Large hydro units, large coal units, large nuclear units, and we needed large transmission in order to bring these power back to where people live. But because of distributed generation, which are much smaller in this, small nuclear units, small solar units, small wind units, you can bring this closer to where people live. And that's where the advantages of microgrid come into the picture, because these things could be very close to residential areas, could be very close to hospitals, universities, where people live, and basically reduce the need for massive transmission systems. I mean, when you go to third world countries, the cost of building additional transmission systems gets to be so prohibitive, so expensive that they can't afford that. And that's where the usage of this distributed generation plays a significant role. But overall, in developed countries, you need a holistic solution, some transmission, some distributed system, some batteries, load control, all of that together.
And then while we have you here talking about microgrids, there was a question specifically to you about, specifically, do you produce electricity and how much storage did you implement? And that's a whole nother conversation about all this energy, storing it as we go forward.
Well, you know, the microgrids comes in different sizes and shapes. In a sense, when we help build some of these microgrids in Africa, you know, we use local resources. There is no thermal generation there, so you use hydro, the river that's near the village. We use lots of solar. We use biomass. So we look into what's available, and that's the beauty of microgrid, because we can localize the solution depending on what's locally available, and then use that. At the university where I'm located, we use you know, about 8 megawatts of natural gas and about 1 megawatt of renewables. But we are in the process of bringing more to renewable generation. Of course, Chicago is not the best place for solar power generation. However, with the control of the load, we can reduce the use of thermal usage, thermal generation usage, and get to that point. But overall, depending on where these microgrids are located, you can get away from using a lot of thermal and localize it. For instance, in some of those islands that I talked about earlier, there's lots of solar energy available, like when you go to Hawaii, there's lots of wind available, lots of biomass. And basically, you can get away from use of thermal generation and supply as much load as you want.
Thanks for that. We have a question here going back to capturing carbon. I know, Tim, you've spoke about capturing carbon, obviously, Catherine as well. Are there examples of significant commercial uses of captured carbon that would avoid sequestration? So Catherine, why don't you take that first? And Tim, if you want to add on to that, feel free.
Sure. And I'll point out that there was a National Academy's report in 2019, which was all about this topic for CO2 and for methane. And the biggest commercial possibility for CO2 is through mineralizing the carbon. You can make commercial products for the construction industry, both aggregate as well as cements used in concrete. So that's currently the biggest commercial use that is being pointed to. Hopefully in my remarks today, I've maybe intrigued some people to think about there is utilization for CO2 in terms of environmental remediation as well, but that's just emerging. Tim, did you want to add something?
Well, yeah, I guess in terms of what's in the money today, you know, what can you make money on today? It's the biggest far and away is enhanced oil recovery. And outside of that, there just aren't many things. And then basically, as you start looking at this, the cost of carbon, you know, if you were to put a carbon tax, for instance, you know, the number of things that you can do to make money with it start to go up. What I had referred to before was actually making a fuel out of it, using the CO2 as a source of the carbon atoms. But obviously that takes then it's not an energy source. You use wind or solar to basically take carbon dioxide and water and convert that into a fuel. But that's going to require a price of carbon substantially higher than I think where we're going to be.
Tim, I'm glad you brought up enhanced oil recovery, because that is, for utilization of CO2, that is the number one thing that people have thought about, but it is a form of sequestration. In enhanced oil recovery, the CO2 is put underground to get more petroleum out of the ground, and the rule of thumb is that about 50% of the CO2 injected in that process remains underground, and the other is recovered with the petroleum, the crude, and then it is recovered and used again. So that is a good way to think about utilization and sequestration, I think.
On the note of carbon, we have a question here that is, what do you think about pricing mechanisms to change the consumption load profile and to encourage resource reduction, reuse, and recycling? In addition to commercial pricing mechanisms, what do you think about the role of carbon taxes? So this touches on a few different areas. If anyone wants to volunteer, feel free to raise your hand. But knowing that it's talking about load profile, I'm going to go to Mohammad first, and then we can take anyone else who wants to address this question.
Yeah, that's an excellent question. But overall, you need a holistic solution. So we need to look into carbon tax as well as load control, as well as the usage of renewable energy in order to come up with the best solution. Carbon tax, I think, is something that is absolutely necessary if the plan is to move the whole country toward net zero and potential for reducing the use of thermal energy. So I think the carbon tax is coming, but in some places in the United States have already started, but definitely it's something that needs to be handled through the market so that you look into ways of pricing it to the extent that individuals get attracted to it. And I think that's the way we are moving overall in the electric utility industry.
Ken, was that you? Did you raise your hand?
Yeah, I did.
Great.
Because I loved Mohammed's answer, but I want to broaden the response. I mean, I don't have a whole lot of content to add to the broader response other than just to encourage us to raise the level of the discourse on this topic to a global level, because this is not just about taxation in the U.S., carbon taxes in the U.S. I mean, we have to figure out a holistic solution globally for addressing this. And that's what makes this type of strategy so difficult, because it doesn't really work across, country borders. And so the broader geopolitical issue is a tough one. And that's going to require addressing it if we're really going to make an impact through, this kind of a strategy.
Yeah. I have one quick follow-up, Dan. If carbon has value or sequestration has a value, either a tax or a carbon exchange, it can influence behavior. It can influence the way that we make decisions about sustainable infrastructure and what we choose to do. So in the areas that we work where there is a value to carbon, it actually can bias or weight the decision toward using a sustainable landfill cover or creating a more nature-based solution that has a carbon benefit. By quantifying that and then having a dollar amount to it, we shouldn't underestimate the degree to which that can change the way that people make decisions or make it easy for them to make a decision which is additive to our fight against climate change.
When we talk about the carbon tax, of course, everybody looks into ways of managing the electric power usage and electric power industry. But we shouldn't forget that a lot of carbon is produced by combustion engines and the current cars. So basically moving the whole country and promoting globally the usage of EVs, electric vehicles, I think is a way of reducing the carbon if that's what we are really serious about.
Mm-hmm. Yeah, we even think about it in terms of how much concrete is used for a project. If you can use less concrete, you're using less carbon.
And I mentioned it earlier, but, we're at this inflection point where now electric vehicles are being considered more mainstream. But for that to really take hold at scale, continued innovations and breakthroughs are required in order to get the cost of battery packs down to the level where you can buy a vehicle that is as inexpensive and it's over its life cycle use as a combustion engine vehicle. And today that's just not true, but it's getting close. So continued innovation is required in order to cross that curve, for those curves to cross.
And to go back to a point you made earlier about the geopolitical climate, and we've talked about climate equity globally. When you talk about electric vehicles being at an inflection point, do we feel like that is domestically, or do we feel like globally electric vehicles are at an inflection point?
it's globally, but some countries are ahead of others. I mean, it's clear that, you know, China is taking the front, and the U.S. is close behind, and you know, other countries are moving more slowly. I don't watch it daily anymore because I'm no longer in the industry, but I think globally it has to happen, and for it to happen globally, it's a mix of policies and technology innovation. It's not one or the other. It's got to be both, because people are not going to, you know, open their wallets to do things for the climate. Few people will, but not everyone. The masses won't. That won't scale.
Yeah, I mean, I think those are all really good points. I mean, we've seen even here, like the subsidies related to buying electric cars and the need for cooperation across technology, developing the battery capacities, but in coordination, you know, with policy as well. We have some other questions coming in here. We have one that's, can you talk about the needed transmission infrastructure changes to cope with loss of system strength and inertia resulting from the increasing penetration of wind and solar? That is a big one. Tim, do you want to take that?
Yeah, so I think what the question is referring to is the fact that, you know, when you have a coal plant, a nuclear plant, a gas turbine plant, there's an enormous amount of inertia of this thing just spinning around, and that provides that's a useful service for the grid. And when you start looking at things like like solar, you don't have that, and so this directly segues into a lot of thinking about how do we build in the high voltage control systems to manage these systems, but also how do we store energy? How do we have other means of building inertia into the system via energy storage? So Ken talked a little bit about energy storage with respect to electric vehicles, but this question directly talks about energy storage just around electricity. Because, you know, one of the amazing things about our electricity system, I mean, it's truly amazing, is the fact that the electricity we produce and consume at every instant in time basically balance. And I mean, just imagine any other system that we use where what you consume and what you produce matches. Like, if, I don't know, wheat, you know, if the amount of wheat you grew every day had to match the amount you ate. I mean, it's just so this challenge of the cost associated with storing electricity is a real issue that where innovation is happening, but more needs to happen.
Also, you know, when you go into distributed power systems in the form of like microgrids and all that, the need for this inertia gets to be less. The inertia gets to be a very important subject when you have a centralized power system, because they're all interconnected to the extent that if you have any kind of disturbance in one location, the entire system will start shaking. However, when you go to distributed system, that issue will, to some extent, will go away. But I'm glad to also report that in the area of power electronics, I don't want to get very technical in this subject, but they have started looking into new technologies that would create inertia to the extent that will serve the purpose as we bring in more renewable energy into the electric power system.
Great answers. We have a question here going into different alternate renewable sources. You know, we've talked a lot about wind, we've talked about solar. We haven't discussed too much about geothermal as an alternate renewable source. And I know, you know, there are certain countries that are definitely leaning in on geothermal more. Leslie, would you like to talk about, given the need to build out a true national grid, do you have any thoughts on using geothermal as an alternate renewable source?
And I think there's probably others that are equally or more competent on the geothermal side, but we always have looked at it as one of the items in the portfolio, but not one that's necessarily pervasive as a overall solution. Similar to what the other speakers have said, we see the fastest growth right now, mostly in the solar and the wind energy sector. And the geothermal, there are some interesting angles in addition to geothermal drilling that are more heat recovery oriented. So at the building scale, especially in a microgrid environment, we see opportunities where There's you can get heat recovery even from waste discharges or from released heat to actually help more efficiently power buildings and move toward a actual net zero at the building scale and at the individual scale. So there's some really interesting innovations in how we harvest and manage heat, but geothermal is just one of them.
I think I'll add that geothermal is an energy production method that works some places, not everywhere, and that's true with so many of the low carbon technologies we're talking about, and so there isn't a one size fits all for every state in the country, for example. So it's just something to keep in mind, that almost every question we ask has a geographic answer to it.
Yeah.
Good point. Good point. Mohammad, you've mentioned quite a few times it depends on your local, regional area. So I'm assuming you would echo that as well.
Definitely. I think what it was pointed out, what Professor Peters pointed out is very important, but also we should keep in mind economics, in the sense that some of these new technologies, sort of new, like wave energy or geothermal, these are very interesting topics, but still they are cost prohibitive. In many cases, the ROI, the return on investment, is very, very long for some of these technologies. I mean, it's dropping for solar, it's dropping for wind. They're getting much more affordable, but for the rest of them, we have ways to go. Unless we introduce new technologies, new innovations to the extent that makes these new technologies, I mean, like geothermal, and as I said, wave and the rest, more affordable, you're not going to see as much adaptation of those, at least for the foreseeable future.
Great answers. The next question is talking about reducing demand in the energy sector. I want to bring up something, Mohammad, that you had in your slides about the urbanization in general as we look forward to 2050. Can you explain, is the urbanization something that's ultimately good for reducing energy consumption, or do we ultimately see more complications with that, with all of us kind of congregating in larger cities and less spread out? And then I'm going to follow on with another question with that, but I want to get your thoughts on that first.
Well, urbanization is going to happen whether or not we like it. I mean, people, as I pointed out, are moving to bigger cities because there are more jobs available, in particular in third world countries. And also, bigger cities are more secure. You know, there's more security available in those areas. And but the problem is that when you move people to bigger cities, you need much more infrastructure, in the sense that many of those cities in the third world countries are not ready to accept such a massive migration of people. And that's why I brought up the issue of managing the energy to the extent that we can levelize the load, educate these people. And it's not only for electric power. You're talking about transportation, water, and all of those. We need to come up with ways of managing those infrastructures to the extent that we can sort of fit it into the fact that people are moving to these big cities and they demand more. So yes, of course, when people move to the big city, there's more concentration of usage of energy in those areas, but the introduction of new technologies, microgrid, levelization of the load, smart grid, I think those are definitely needed to manage the these usage of electricity in very congested areas of the world.
Kind of related to that, we have a question here about reducing demand in the energy sector, but in particular, how do we get land use decisions to be made better to conserve energy, water, and materials? And how should engineers get more engaged in influencing these decisions? So this speaks a bit to what Mohammad was just talking about, but Leslie, I think this is something you addressed in your beginning talks as well. So Mohammad, do you want to address that, or should we go straight to Leslie?
No, Leslie.
All right, Leslie.
Yeah, I think instead of land use, I would probably think about it as that alignment of public policy with technology. And we've all touched on it in different ways. The way that policy actually drives or enables the technical solutions that we'd like to have, right? And public policy could include things like master planning and anticipating impacts associated with urbanization on water, environment, the grid, all the different pieces that go with it. And the more that we get alignment between public policy and climate change related activities and carbon management, as well as the adaptation, the more likely that we'll be able to influence land use related activities and build them into how cities are actually designed and built. I agree that some level of urbanization is probably a given, but then the next step would be how can we urbanize in a way that is of the least, has the least negative impact and the most beneficial impacts toward climate. But building policy, and this is often policy at local, state, provincial, national, and global level. So you need every level of policy aligned, otherwise very difficult to implement.
Yet another wonderful comment about the need to coordinate across policy and technology. We have some questions coming in here that I think will be good for Ken and Tim, related to electric aircraft. So we've talked a lot about electric vehicles related to cars. I know we've talked a lot about aircraft separately and like drop-in fuels and things, but there's a question here about what are the potentials of achieving net zero in the I just skipped over that. Given that air transportation generates lots of CO2, what does the panel think about electric aircraft? Do you know of solutions for large passenger aircraft? So let's first go to Ken and then we'll go to Tim.
Well, first, let me just kind of provide a couple of facts. The airline industry contributes roughly 10% relative to the other modes of transportation to greenhouse gas. So it's not an enormous percentage of the whole pie. By far, the largest contributors are light and medium duty and heavy trucks. So it's still important to address. But we have to keep it in that context. I'm not aware of any major initiatives to address electric aircraft for large passengers. However, there's a very, very significant effort underway to develop electric small vehicles, flying vehicles. They're called them electric vertical takeoff and landing vehicles. And there are many of the airlines and many startups are developing these technologies to power relatively small passenger aircraft with electric motors, with lighter weight materials, and taking advantage of new battery chemistries that have very high power densities so that you can travel medium distances. You're talking about distances that are really too long to drive and kind of too short to consider large passenger aircraft. So think 300-400 mile range and even 200-mile range, like San Jose to San Francisco or New York to Washington, D.C., those kind of ranges where people sometimes drive, but it's too long of a drive for it to be comfortable. Those are perfect for electric aircraft like these VTOLs that are being considered. They still face a number of hurdles in terms of certification and safety certification and also FAA certification. But the technology is moving to the point where it's relatively proven. So that could be very, very interesting because it could take a good chunk out of that 10% because a large fraction of air travel is in that sweet spot where, it's relatively short distance and you don't have to have a big, large aircraft in order to go those distances. So I'm pretty excited about that. I'm kind of personally watching that space to see how it evolves and develops.
I love it. I'm going to personally watch that space too. It's exciting. And Tim, I know you do a lot of work with sustainability in the airline industry. So electric aircraft, is that in our future? And also throw it out to you, what other sustainable future for aircraft do you see?
Yeah, so I think to think about how do you take the aviation industry and get the CO2 out of it? There's kind of two pathways that I could think of. One, we talked a little bit about earlier, where you electrify the aircraft by you make a renewable fuel, right? You use solar energy or wind or some other renewable source to make a fuel. In other words, to charge a battery. That battery happens to be a fuel, and that fuel could be a drop-in, like today, that looks a lot like Jet A, or it could be something else like hydrogen or ammonia. So that's one way to do it. And that way actually scales nicely across all different sizes and platforms of vehicles, particularly if you take a fuel that's drop-in. Now, if you actually want to electrify the aircraft, like Ken said, I don't think it's feasible to think about large-scale aircraft ever being all electric. They're just massive. But you can do some really cool stuff when you hybridize. And so NASA and all the aircraft engine manufacturers are working on this, because if you think about what an airplane engine does, when you design the airplane engine, you size it to take off. That's where the massive amount of power, but most of its fuel burn is cruising along where you need much, much lower power. And so when you hybridize, what you basically do is rather than having your jet engine do everything, you essentially run it like a power plant, where you essentially have a bank of batteries. You might be discharging batteries to take off, and then you're running off the power plant for cruise, and so forth. And so there's a lot of really neat things you can do to completely revision what the overall aircraft looks like when you hybridize electrical systems with the kind of traditional gas turbine power plant.
Really fascinating stuff all around. Great answers. We have a question here, a bit of a general question about how can engineers help raise awareness of equity issues as we rapidly expand adaptation efforts? And I'm going to address that to Catherine. And then also, I want to expand that as well in terms of education efforts for the engineers that we're bringing up through our system about how we can raise awareness of our engineers that are growing up and developing more sustainable technologies. So go ahead, Catherine.
Okay. This is a really important point, because the impacts of climate change are not evenly distributed across communities. And I think that in the United States, for example, we've seen that often marginalized communities are disproportionately affected by, for example, flooding, coastal impacts, strong hurricanes, and their ability to be resilient and recover from these impacts is difficult. So there are important, I'd say, data science tools that need to be developed, monitoring tools. We value and understand things and can take action when we have data. So that is one engineering point. But I just am reminded of that phrase from the 1970s about think globally, act locally. The climate change is challenging because it's a global environmental problem, and climate change is challenging because the impacts are very local and locally felt, and solutions are different at different spatial scales. And so I think that is something that we need to constantly remind ourselves about. Deanne, did you also want me to talk about your second question?
Yeah, and if anyone else wants to tackle this as well, we can. But obviously, there's so many engineers in industry working on these problems, addressing climate change from an engineering perspective, obviously in academia, but we're also focused on educating the next generation. And how has the engineering response to climate change made its way into the university system, and how we educate our next generation of engineers to tackle these problems?
Yeah, just as engineers and researchers have turned our attention to low carbon technologies, we should be preparing our students for this net zero future. And an entire industry has emerged in sustainable energy management and consulting and climate risk. It's a multi-billion-dollar industry worldwide, and for example, the decarbonization technologies industry is just starting to emerge. I mentioned Climeworks. There are other direct air capture companies that are emerging, carbon capture companies that are emerging. So students need to be prepared for these new technologies, and they need to be prepared to help their employers by being knowledgeable about resilient infrastructure, risks, hazards. I see this as a call to action. Curricular reform, new teaching materials, throw out some of those old textbooks that have examples that are no longer relevant. For me, it's a new way of thinking about faculty hiring. Every single faculty hire we do, I think about how these professors are going to engage students. So I'll leave it at that.
Yeah, and I know, Mohammad, you wanted to address that as well. Go for it.
I'll say, I think if we start thinking about net zero in the university, it's just too late. You have to start from elementary school. You need to educate people from the very early stages to understand that they need to conserve energy. They cannot waste it of any kind. So a lot of these technologies and new ideas, if we start at the university, we have lost them. We have to start much earlier. So elementary school, high school, those are the areas that we need to bring in the new ideas and make sure that the next generation understand that those matter, those issues really matter.
I couldn't agree more. At Future Engineers, we do K-12 engineering education. So we work every day with contests and challenges, and we're seeing increased demand for climate-related projects, climate-related activities, climate-related education. I agree. We need to start young with awareness of this, but also as we, in the university, we talked about these skills from data science to, carbon capture technologies and all of these things. I don't think there's any sector of engineering that doesn't have a path forward with sustainable technologies, right? So, so great stuff all around to here.
Can I add something to that? So,
of course.
I love that. I mean, start young, yes, and educate, yes. But my observation is that, and I think all of us see this, is that it's not just young people. I think it's grown-ups and it's policymakers and it's business people that have, aren't looking at this problem the right way. And so I'm not giving an answer as a panelist. I'm posing the broader dilemma, the broader problem, which is how do we educate everyone better? How do we do a better job of educating grown men and women about their choices and the importance and the urgency of this issue? Because and quite frankly, in my circle of people that I interact with, young people get it before older people do. And so I think that's the bigger challenge, is how do we raise the awareness and sense of urgency of, full-grown people?
And one other sort of perspective, I think that what we're talking about here is actually raising awareness so that it spurs development to create a whole body of science or a whole new way of doing things. And it's all the disparate fields that we all represent and a few dozen more or hundreds more. But I'd like to think that we look back on this 10 or 20 years from now and say that this created a whole new body of science that collectively is the new carbon negative, way of doing things, and which is the engineering and all of the other, the textbooks that would get written and the PhD theses that get defended, and then ultimately the way the guidance documents are written for how people engineer our cities and everything else we do.
Yeah, if I can add one more thing to that too, just thinking about just broad education and awareness, I think one of the things that's, kind of stretches our brain in new ways about the climate change issue is just that it's such an interconnected system and it's a global system. So, I mean, if you think about other forms of pollution, like if you dump something in the water, you can kind of figure out the people that are affected are those downstream. Or if you have a car that's spitting out, NOx, which is bad for people's lungs. You can kind of figure out where that goes and who it will affect. The CO2 problem, it's a global issue, right? And so what we do, so in the whole, everything's interacting with this issue. So I mean, you've probably heard how there's these biofuel mandates meaningfully trying to help, which have the impact of rainforests getting cut down to grow palm oil, whose overall impact is not healthy. And so just understanding the global nature of this and how interconnected it is. And so it's wonderful for the city or the state to reduce its carbon footprint, but ultimately what matters is the global CO2 emissions. And it's sometimes not obvious understanding how these things interact such that our behaviors either increase or decrease the global climate problem.
I think you're so right. And when you think about climate, there's technology, there's public health. I mean, there's so many layers of it. And you're right, it's so interconnected. And it almost sounds like, based on these responses, there's a whole other panel in store about science communication with the public and about, there's so many different avenues we need to take to effectively, get the public to be educated, but also change consumption habits too, right? So all really, really good points. We are going to take a question going back to carbon capture. We've got a lot of carbon capture and net zero questions here. So what are the potentials of achieving net zero in the materials used in engineering, such as cement, asphalt, and silicon chips? And I'm going to take that to, who wants to take that? Leslie, do you want to take that?
Net zero and carbon. Well, when we look at net zero, I'll use buildings as an example. So like an office building is in the design of the building, you could aspire to be a net zero, but that would mean you have to offset the energy that you use, you minimize what you use, and then you offset it through the all of the actions that you take, as well as sometimes people offset offsite by installing more solar or doing other things to create a package. And that can go to water use, it can go to any number of things. So the technology is evolving so we can get there. The cost profile is still expensive to do the sort of the ultimate in terms of achieving that. And so it's coming. I think we're working on it. In the broader sense of that question, I don't think we can turn concrete in and of itself into a net zero, but we can minimize the amount of concrete that's used and substitute with other solutions in some cases that are much more advantageous from a carbon perspective, which would bring me back to this decision process of both financial and policy related of how do you actually add carbon to the equation? How do you add it into the decision process to make it more desirable, for instance, to make a home or even a building out of timber construction versus concrete? We can do it. It's attractive. Can we make it more desirable by aligning policy, finance, and the preferences of the various developers or those that are spending money? The one other part that's starting to take more hold is most large corporations have a focus on ESG or a focus on the environment and sustainability and have their own sustainability goals. That becomes yet another driver for that type of decision making.
Yeah, and following on that, an example was given of France. It was stated that France has achieved net zero in its generation of electricity through a combination of nuclear and hydroelectricity. What are the barriers for other countries to follow France? And I know this brings up nuclear, which I know has not been talked about too much here. But Tim, do you want to chat about that in terms of net zero and how are they able to achieve that, and are there barriers for us doing the same?
Yeah, I mean, nuclear is a whole thing in and of itself, which is driven just as much by the regulatory regimens of the countries it's in. You're seeing massive growth in nuclear in countries like China, You're seeing Germany essentially getting out of the nuclear business when they happen to be right next to France. So it's certainly doable. It's just a matter of whether there's the public will. And also, like we're finding in the US, I mean, the state that I live in, the state of Georgia, is the site of the only new nuclear builds in decades. And there's just significant challenges around the workforce and so forth. So I think to me, the answer around nuclear is, instead of going big to smaller, these smaller modular type reactors, it remains to be seen whether we can tackle the non-technical regulatory issues. On the hydro side, I don't see the developed world building any major new hydro plants. I mean, we're starting to blow dams, right? I mean, California, right? Northern California will be getting rid of a dam in the next 5 years, I think.
And is that because of the aging aspect of it,
Well, I think it's the overall life cycle assessment of what do dams do? What have they done to indigenous people? In many cases, they've just devastated sort of the culture of the local people, where people would assemble to fish. Those are now underwater, and so, really, I'll just say very complex issues around hydro. I just in a million years, I couldn't see a major new hydro project going on in this country.
Well, I believe we have to come up with a very specific definition of net zero as a proceed. In some places, getting rid of thermal, 100% thermal will be possible. In some other places, because of social and economical issues, it may take a long, long time before you reach the net zero. So we have to live with that fact that it's globally getting to net zero and globally getting rid of thermal energy may take a long time. We're going to move in that direction, but it may not happen in the near future.
But I think it's a good example of where, a combination of a lot of little steps begins to change the discourse and the culture.
Definitely.
So the devices we sell to, millions of people, letting them know that these are devices that are not adding to the CO2 footprint. So they feel good about buying these devices and using these devices because we've done the analysis to show that it's not contributing to the problem. That's an example of how you're chipping away at setting the right culture and the right mindset. I think we just have to continue to do things like that, and not get lost in trying to boil the ocean and solve the problem in a few years, because we created this problem over decades, and it's going to take decades to solve it. I know we don't have as long as we'd like, but little things matter, and we have to continue to have momentum through these little and some not so little acts that change the mindset and the culture, because then it'll lead to better policies, because the mindset of the population will be behind the right policies to make bigger things.
Yeah, and I think actually this goes back to the earlier question around, making net zero asphalt or silicon chips or concrete. I think there's some really exciting things happening in engineering as we're trying to, around this whole circular economy idea that, we've built our economy around these consumptive ideas where you manufacture it, you build it, and you trash it. Well, what if we were to design these things so it was very simple and easy, and we designed them to be recycled and to be reused? And there's some really, and there's some fascinating chemical engineering, broader engineering problems around how would you engineer materials and processes to be circular? And I'm really personally excited about what's happening in that space.
Plastics in particular, Tim.
Yeah.
So Ken, you mentioned, transparency of products that, are net zero, making people feel good about when they're spending that money, that they're, that they're not contributing to climate change in those ways. What about the other argument, which is making products that are gross offenders really expensive, or making fossil fuels a lot more expensive? What do you guys have any thoughts on that, about kind of the bottom dollar there, and how far prices can be pushed to make it to kind of control the consumption of these things?
Well, I think the in some ways that's already been done. It's sort of built into into the penalty you pay when you buy, for example, gas guzzler vehicles. You have a gas guzzler tax, and so there are some cases where we've seen that, but it doesn't really dissuade people. If they really want it, they'll just pay for it. The economic delta has to be much bigger than it has been in the past. That doesn't, could that happen, and would it actually make a difference? Possibly it would, but we haven't had the political will to put that into place, at least not at big scale. I haven't seen it.
Does anyone else want to chime in on that economic delta? I know, for example, the cost to fill up your car in other countries is significantly higher.
Yeah, one other issue is that when it comes to net zero, you will see that the United States is not ahead of the game, in the sense that a lot of energy development projects in developing countries, in particular in the African continent, are already net zero. And in the sense that you go to some of those villages where they have nothing. So when you build the energy infrastructure, you build solar, you use water, you use biomass, you use whatever is available there, but there is no fuel available. So basically, you start with a net zero project. Now, it's going to take a while before it gets to developed countries because they already have a massive infrastructure in place. Now, to what extent we get a chance, and it goes back to the issue that I raised, that it's all based on economics, how much you can afford to change. And you'll see that you're taking big steps here, but you'll find out that those underdeveloped and developing countries will get to be ahead of the United States at some point when we think about net zero.
So we see some questions coming in about kind of China has passed the US as the largest CO2 emitter. Once again, going back to the geopolitical coordination of addressing climate change. And in general, talking about kind of, do we like it feels like the ship is going. Can we readjust this? Can we turn this around? And I think it just speaks to this broader idea of like, if we all put our thinking caps on to try to look towards the future and 2050, like I would love to hear from each of you, like what you see in that future that is the way we've addressed climate change and we've got out of the solution. Like what are the engineering solutions that you feel are at the crux of that for us to really try to turn this ship around and really develop sustainable technologies? So it's kind of a big question, but I know we're getting towards the end of the session. So I wanted to open this up to all of you. Catherine, do you want to take a stab at that first? Some of the things that you see that need to happen?
I just want to start by saying that China has not passed the U.S. in per capita emissions, and that's an important.
That is a very important point.
That's a really important point, and it's so the United States is both a big emitter and a big per capita emitter, and so we play an enormously important role in this global problem. So I'll leave it there and see what the other panelists want to add.
And I'll just add to that I when people talk about the China passing the U.S. as the largest CO2 emitter, that's true. But if you look at why we are where we are today, the total number of the amount of CO2 in the atmosphere, the U.S. far and away has been the largest. If you just sort of integrate over our contribution, it's the United States. And so I mean that needs to be part of our public dialogue as we're talking about these global interactions.
Those are both really good points. And I think if we're talking about that, we're focusing on the US and what we can do in our engineering practices that also impact the globe. So when you guys think about it, big picture, in 30 years, how society is going to look different so that we can address this problem. What are those big ticket items that you guys want to, that you envision, that you see are really going to help solve this?
Well, I'll end where I started, which is, I think it starts with making a commitment from companies and from individuals. And so I'll just speak from a company point of view. Amazon's made a commitment. We call it our climate pledge, reaching a net zero carbon stance by 2040, having 100% renewable energy by 2025, having 100,000, electric delivery vehicles on the road, and our climate pledge fund. So if you look at these commitments, and if every company had an analogous set of commitments to make a difference like this, which means putting their intellectual horsepower behind these commitments, creating the right kind of culture in their company to care about renewable materials and renewable energy, that's going to put a big dent in this problem, because the economy is primarily driven by commercial industry. And if every large commercial industry company had a commitment behind climate change that was analogous or better than this, we would get there. So I hope that we're setting an example that others might follow.
I'd like to add to that, because I think Ken's point is excellent, and I actually see it across the board with companies that we work with, that they are increasingly adding to their commitments. So we've got this groundswell of activity. But just one or two other points. It wasn't that long ago that we all went to working remote because of a global pandemic. And we saw just a huge acceleration in innovation and technology and the way we apply technology. In many parts of the world, people stopped commuting overnight practically. And it shows that there can be just incredible at such a rapid pace. And then the third part is, I think if we look back a few years from now, we'll see that the amount of data that we have now, our ability to understand the natural and the physical world, is moving incredibly rapidly. We have sensors that we never would have had. We used to spend, in my water space, we used to spend all our time extrapolating from just a few monitoring stations. Now we have clients deploying tens of thousands of sensors across an entire watershed. So the amount of data that we'll have and the amount of insight we can gain from that is something I don't think we've even fully taken advantage of yet. We're just starting.
I think if you look at if you're interested in a very big picture, spending a lot more money on R&D in order to make some of these new technologies more affordable, so that people can use them. When we talk about many of these technologies, it's not readily available yet because of the cost. It was pointed out earlier, the cost of battery and all of that perhaps makes EVs more expensive than or not as affordable as we expect. So spending more money on R&D, spending more money on education in order to make the individuals buy into these new technologies, and spending a lot more money on AI. I think these are the issues that we need to look into for the future in order to make net zero a lot more affordable.
And we'll do Tim and then Catherine. Tim, are you there? Tim, do you hear me?
Oh, I'm sorry. I thought you said Ken. Sorry about that. Sorry, Ken.
No, we're going to go Tim and then Catherine. Yeah, yes. Big picture.
Yeah,
what do you think are the important?
I'm embarrassed. I think so. First of all, I'd say it's deeply concerning what's happening right now. But I also think that we should not underestimate just how much innovation is getting injected into this space. And it's one of these things where you always you overestimate how much you can do in 1 year, but you always underestimate what you can do over 10 years. And so if I just look at what's happening in the cost curves around solar, it's a great story. Or wind, the dominant source of new capacity in the US for the last 5 years has been renewable energy. That number is still too small, but I think there's a lot of really exciting things happening. And so just really thinking about how engineers can sort of get out of our cubicles, and these are technical problems, but they're deeply social problems, and really understanding those broader social constructs understanding the job impacts, the equity impacts, I think we can be much more effective and really move the needle. And I think we're going to see real motion in 2030, real effects.
And Catherine.
I think that I'd like to remind us all that even without innovation at this moment, we have an array of existing technologies that can be put to bear on this problem. And this has been said even 20 years ago, that we have already tools that exist that can be used. We just have to do it. And so I don't see, when I hear energy systems analysts doing their analyses, I don't hear them saying, we don't know how to solve this problem. What I hear is there's a broad array of ways to solve this problem. We need them all, and we should get down to business.
Really good answers all around. I just want to say thank you to all of our panelists. Thank you, Ken. Thank you, Leslie. Thank you, Catherine. Thank you, Mohammad. Thank you, Tim, for sharing your expertise with us and taking so many wonderful, thoughtful questions. Thank you to everyone watching at home for submitting all of your questions. This has been a wonderful forum, yet again, all about engineering responses to climate change. And I'll just end with this final note, which is, you know, I have two little kids. I have a 3-year-old, I have a 6-year-old. And, you know, when I was little, I dreamt of flying cars, and I dreamt of Jetson machines that could brush my teeth, right? But now, you know, what we dream about is just developing technologies that are going to make their future a brighter place, right? And so I just think just another call that the time is now. There is all kinds of urgency. There is all kinds of motion. And no matter what sector of engineering you're in, we need you. And so just a nice reminder to all of us that we can all use our engineering to make this world a better place. So thank you so much for tuning in. Thank you for being a part of this, and have a wonderful rest of your evening.
Thank you, Deanne, and thank you, panelists. That was an excellent job. You brought much needed insight to a very important topic. And to use the old movie metaphor, there are a lot of questions laying on the cutting room floor. And so I think if any of you have questions that are of particularly burning interest to you, you should feel free to reach out to any member of the panel and get their takes on it. I would also be remiss in not thanking the outstanding committee that we used to organize this particular session. Their names were given and affiliations. So I think it's on page 16 of your virtual book. I'd encourage you to look at it, and thank you for them, because it wouldn't have happened without their help. So let me then just end by thanking our entire team, you know, the panel, the committee, et cetera, Deanne, our staff, who are doing just an absolutely wonderful job. And with that, let me turn it over to our president, John Anderson, for some concluding remarks. John?
Thank you, Al. What a timely discussion of engineering responses to climate change. I cannot think of a better group to discuss strategies and tactics to reduce carbon emissions and mitigate climate change. Now that we have reviewed a range of possible actions, we should continue to develop these ideas to sustain the planet for future generations. Thanks again to everyone on the panel, and thank you, Deanne Bell, for again doing a great job for moderating the discussion. Really appreciate it. And I thank the attendees for the excellent questions posed to the panel. When we think of climate change, COVID-19, and other global problems, we should emphasize the creativity that comes from the engagement of engineers, from both senior and junior professionals. Engineering is alive and vital. As NAE members Samuel C. Floorman eloquently captured in the engineering mindset of his book, The Existential Pleasures of Engineering, we are restless, we have an irresistible urge to dip our hands into the stuff of the earth and to do something with it. There's a lot of complaining these days about our situations, but we are in a position to do something about it, remembering that engineering is a verb. As we wrap up today's meeting and the public portion of this year's annual meeting, let us carry with us the excitement of doing something for the betterment of humankind. When you turn off your screens, please make a point to reach out and connect with another member. Our conversations motivate us They keep us connected, and creativity will arise from such conversations. I am honored to work with all of you in our efforts to contribute, and I am grateful for your generous gifts of time, expertise, and financial support in service to the NAE and the National Academies and the nation. I would like to acknowledge the efforts of the committees that help plan and bring to life the annual meeting, and the staff whose work made this a remarkable gathering under very difficult circumstances. Thank you very much. I remind you, the members, to attend the section meetings taking place tomorrow. I will be attending the Section 3 meeting and stopping by a couple others to provide updates and listening to what you have on your mind. Each section meeting will have a visit by one of the 3 officers. Please stay safe and healthy, and I look forward to seeing you in person in the coming year. It will be a good year. Thank you again for being with us. Good night.